What's up guys, it's Simon Fiaz and today's video is on AQ A-Level Chemistry 2020 Paper 1. So, first question, Born-Haber cycle doesn't want me to fill it in, it wants me to calculate the for electron affinity of chlorine. So, I'm going to set the enthalpy of formation equal to, so I'm going to say minus 828, that's going to be equal to everything else. Okay, now, this is obviously the atomization of strontium, this is the atomization of chlorine, this is the first ionization energy of strontium, this is the second first ionization energy of strontium, and this is the electron affinity of chlorine. So it's going to be minus 828 equals 164 plus 121, but because I've got two chlorines, it's going to be 121 times by 2, so 121 plus 121 plus the first ionization energy of strontium plus 548 plus second ionization energy of strontium 1060 plus the enthalpy of lattice formation plus this, it's 2y, this electron affinity, plus 2y minus this 2112. Minus 365. I think the difficult part of this is understanding for chlorine, because I've got two chlorines, the enthalpy of atomization of chlorine is going to be 10 by 2, and also the electron affinity of chlorine, since I've got two chlorines, is going to be 2, so therefore it's 2y. Draw a line from each substance to the enthalpy of lattice formation of that substance. So you just split it up into its ions, so you got Mg2 plus Cl minus, 2Cl minus, Mg2 plus O2 minus, and Ba2 plus 2Cl minus. So the one with the highest enthalpy of lattice formation is going to be magnesium oxide, and the second highest is going to be this, and therefore barium chloride is going to be there. 1.3 state why there's a difference between theoretical and experimental values. It's always going to be about covalent character. It has covalent character as well as ionic bonding. What has covalent character should be fine. Considering why the enthalpy of hydration becomes less exothermic from lithium to K+, less exothermic. Well, what happens to the ion size? Well, the size from Li plus to K plus, the size of the ion increases, hence electrostatic attraction between metal, ion and oxygen, delta negative of water decreases, because remember it's hydration between water. 1.5 calculate enthalpy of hydration in kilojoules multiplied minus 1 of bromide ions. So calcium bromide, CaBO2, it's going to go 2, and that's obviously solid. Ca2 plus aqueous plus 2Br minus aqueous. And I've got its gaseous states here. Actually, that wouldn't work. But hopefully you get the point though. And obviously I want to find the enthalpy of hydration. I know the enthalpy of solution is minus 110. Enthalpy of lattice formation of calcium bromide is this. So enthalpy of lattice formation is when I'm forming this lattice formation. So it's here. That's minus 2176. But I want to go this way. So it's going to be plus 2176. Enthalpy of hydration of calcium ions minus 1650. 1650. I always find enthalpy of hydration of bromide ions. So what I'm going to do is, because this Hess's law cycle, the total enthalpy change is independent of the route taken. So I'm going to say minus 110 equals 2176 minus 1650 plus 2y. You should get minus 318 kilojoules per molar power minus 1. It's not too complicated, you just need to practice these kind of questions and look at 3 marks for that. Question 2.1, give the meaning of the term relative atomic mass. Definition question. So, it's the average mass of an atom of an element on the scale an atom of carbon 12 is 12. 2.2, sample of chromium contains isotopes that has a relative atomic mass of that. Calculate percentage abundance of each of the other 2 isotopes. This one's a very tricky one. You can see it's worth 4 marks. The first thing I would do is I know the relative atomic mass, 52.1. And that's going to equal 2. And I also know the sample contains this much of the 52 isotopes. So I can say 52 times by 86.1. And now what I'm going to have to do is either let 50 or 53, let one of them equal x. So in this case, I'll let 53 equal x. So I get 53x plus 50. Now what will the x in this case be? Well, I already know 86.1. I know the total must add up to 100. So 100 minus 86.1, 13.9, 13.9. And I've also got this x here, so it's 13.9 minus x divided by 100. Times by 100, 52.10 equals 52 times by 52 times by 86.1. 4477.2 plus 53x. 50 times by 13.9 plus 695 minus 50x. 53x minus 50x is 3x, so 5210 equals 4477.2 plus 695 plus 3x. And now I'm going to do 4477.2 plus 695, and then I'm going to do 5210 minus my answer, and then I'm going to divide by 3. And I get x equals 12.6. X equals 12.6. But don't rush now, because it says then calculate abundance of 50 CR. Well, 50 CR is 50 bracket 13.9 minus x. So it's just going to be 13.9 minus 12.6, which is what? That is going to be 1.3. So 50 is going to be 1.3%. Yeah, 53 is just going to be x, which is 12.6. Perfect. Yeah, that's fine. States terms of number of fundamental particles, one similarity, one difference between atoms of 50 CR and 53 CR. Now, because they've both got these same things, I already know they're going to be isotopes. And if they told us it, I feel like most students would get this correct. If they didn't, so it's isotopes, so they have the same number of protons. One similarity, they have different number of neutrons. That's it. Give 2 reasons why it's necessary to ionize isotopes. Okay, well, because the ions will interact with and be accelerated by an electric field, and also ions will create a current when hitting detector. The ions interact with accelerated by electric field, create current when hitting the detector. Question 2.5. Calculate time for 53 CR plus ion to travel down the flight tube to reach the detector. Okay, so okay, so I need to find out. Basically, what I need to do is, because I know velocity is distance divided by time, time is distance divided by velocity. I've got the length of the flight tube. I need to find velocity. In order for me to find velocity, I need the mass. How do I find the mass? So that's what I'm gonna have to do. So find out the mass of the ion. So it's going to be 53 divided by 1000. Actually, no, it's going to be 53 divided by Avogadro's constant, and then divided by 1000. 53 divided by 6.022 times by 10 to the power 23, then divided by 1000. I get 8.8 times by 10 to the power, so 53 divided by 6.022 times by 10 to the power 10 to 23 divided by 1000. 8.8 times by 10 to the power minus 26. 8.8 times by 10 to the power minus 6, and obviously this is in kilograms. And how do I know this? Because if you read the question, it says it wants mass of the ions in kilograms. Okay, now we've got that, I can quite easily find out velocity. Velocity is just going to be, if I rearrange this equation, 2ke divided by m square root of 2ke divided by m, which is just going to be the square root of 2ke. Ke is that. It's going to square root of 2 times by 1.102 times by 10 to the power minus 30 divided by my answer. I get a very large number. And then what I need to do now is, I know velocity is distance divided by time. Show the examiner of me rearranging it. So therefore this time is distance divided by velocity, and distance is 1.25, so it's just going to be 1.25 divided by my answer, 7.90 times by 10 to the power minus 7. So for 5 marks, I think that's pretty nice. Obviously, it's going to be very specific. The mark scheme, you need to show velocity, distance divided by time, maybe rearrange it as well. But yeah, the only hard part was realizing you have to find a mass of the ion. Then you can quite easily find velocity, rearranging it. Then you can rearrange the equation, find time, and yeah. Question 3: draw across on action figure 2 to show the second ionization energy of silicon. So remember, with silicon, it would actually, so it'd go here, and then obviously it's going to drop here. So across there, 1580. Identify the element period 3 from sodium to argon that has its highest second ionization energy. sodium. Reason being is because it's got a high nuclear charge, got the positive charge. It's also very small. Give me an equation for it. So Na plus gaseous, Na2 plus gaseous, plus C minus. Na plus gaseous or Na2 plus gaseous plus C minus. Explain that atomic radius decreases. So the number of protons increases, or you can say nuclear charge increases, whilst the shielding is similar. That's it. Very specific. Number of protons increasing while shielding is similar, and therefore the atomic radius will decrease. Identify the element from sodium to chlorine at highest electronegativity. It's going to be chlorine. Phosphorus burns in air to form phosphorus 5 oxide, given equation of reduction. Phosphorus plus 5O2 P4O10. P4 plus 5O2 to form P4O10. Question 4. State the meaning of the term weak acid. When the acid slightly dissociates in water to form ions. That's going to be the nice part though. The next couple of parts for this question, I can just tell are not going to be as easy compared to this. Acid slightly dissociates in water to form ions. Give an expression for Ka. This is pretty nice. So square brackets K2 C2H5 COO minus C2 H plus as well then here, divided by concentration C2H5 COOH. That's what it should look like. Just remember Ka square brackets. Now if I go to 4.3 and 4.4, okay, so 4.3, a student dilutes this much propanoic acid by adding water until the total volume is this. Calculate pH of diluted solution of propanoic acid. So first thing I'm going to have to do is the dilution factor. So it's going to be 0.500 times by dilutes 25 until total volume is 100. That's what I'm going to have to do. I get 0.125. Now what is this? This is not the moles. This is the new concentration. And that's really important that you know that. Because the first time I attempted, I thought it was the moles. Yeah. Which makes sense because that's the volume and then that's the concentration. But I'm just trying to find the dilution factor. So what's the new concentration I have? Calculate pH of the diluted solution of propanoic acid. Okay, so I know Ka equals this, that. But because I've only added dilute propanoic acid by adding water, it's not going to be impure, it's going to be pure. So I can say Ka is equal to concentration H plus squared divided by C2H5 COOH. Concentration H plus equals square root of Ka, which is 1.35 times by 10 to the power minus 5 times by 0.125. pH is minus log 10 of my answer. I get 2.89. That's simple. Question 4.4. Buffer solution with pH of that is made by dissolving X grams of sodium propanoate in a solution of propanoic acid. The final volume of buffer solution is that, and the final concentration of propanoic acid is that. Calculate X in grams for propanoic acid. Ka is that. So first thing I can already see is that I can find out the concentration of H plus ions. It's just going to be 10 to the power minus pH. which is just going to be 10 to the power minus 4.50. That's a nice mark, a nice way to start the question. Now I need to really understand what's going on. A buffer solution pH data is made by dissolving sodium propanoate in a solution of propanoic acid. The final volume of buffer solution is that, and the final concentration is that. Calculate X in grams. So what I need to find out is, if I do the K expression again, H plus, but this case is not pure, it's not K is equal to concentration H plus squared, because I'm dissolving it now in some sodium propanoate. So H plus C2H5 COO minus divided by C2H5 COOH. Okay, so I need to find out the concentration of sodium propanoate, because once I've got that, I can find out the moles, and then I can find out the mass. Yeah, so I need to rearrange it to get this. So it's going to be Ka times by concentration of C2H5 COOH divided by concentration H plus. And that is equal to the concentration of C2H5 COO minus. I've got Ka. I have got the concentration of propanoic acid, the final concentration 0.250. I've got the concentration of H plus sign. So all I need to do now is substitute my values in. Obviously, you should show it in the exam, but I'm just going to put in a calculator. It'll take just a waste of time, really, if I just draw it out. I think so. That times by 0.250 divided by 10 to the power minus 4.50, concentration H plus ions. Now I get the concentration of C2H5 COO minus, and that is equal to 0.106726871. But I want the mass of it. So what I need to do now is, I know this concentration, I can find out the moles. Moles is the concentration of 0.106726871 times by the volume. Final volume is 500 centimeters cubed, so 500 divided by 1000. I get the moles, and then I know moles is mass over mR. Therefore, the mass is going to be my moles, my answer in my calculator, times by the mR of this, of sodium propanoate. So it's going to be my answer times by 12 plus 12 plus 5 plus 6 plus 12 plus 16 plus 16 plus 23, and I get 5.12. 5.12. It's not that tricky compared to some questions I've seen in buffer calculation. Obviously this is still pretty tricky, but it's not that tricky. Question 5, can't go through that because it's all about complex signs and that. Question 6, draw cross X on appropriate axes on figure 3 when the mixture reaches equilibrium. So when the mixture reaches equilibrium, it should be something like here. Obviously, but you can't put it, you have to put it on the appropriate axis. No, you can't put it just here. That won't work. So here should be fine. 6.2, so now Kp and all of that. And 0.230 mole of carbon monoxide is mixed with hydrogen in that ratio, allowed to reach equilibrium. At equilibrium mixture contains this much of carbon monoxide. Total pressure is that. Calculate the partial pressure. So first thing I can do is find out the equilibrium moles of hydrogen, and I can do that quite easy because it tells me it's a 1 to 2 molar ratio. Equilibrium will contain this much of carbon monoxide, so it's just going to be 0.240, 0.124 times by 2. Then what I can do is, then I can work out the total number of moles. And I know 0.230 moles of carbon monoxide is mixed with hydrogen. So the total number of moles is going to be 0.230 plus 0.240, 0.47. Then what I want to do is I want the partial pressure of hydrogen. So what I'm going to have to work out is the mole fraction of hydrogen. And that's going to be very easy. It's just going to be 0.240 divided by 0.470. I want it in kilopascal, so times by that number. And you should get 5310 kilopascals. This is a bit of a weird question. Very weird question, because it's not your average question where it's like find out the equilibrium mode or calculate the mole fraction. It wants me to calculate partial pressure, and it's giving me, it's just not a normal question. 6.3 given expression for equilibrium constant Kp. Kp curly brackets, remember? So it's just going to be product or reactant. So it's going to be, has it given me equation? Yes, it has. So the partial pressure of methanol, partial pressure of CH3OH divided by partial pressure of carbon monoxide times by the partial pressure of hydrogen. But the key thing about hydrogen is we've got 2 moles of it, therefore it must be squared. And these little tricks you need to be able to spot. Then it says state the units. Well, the units, I'm working with kilopascal, right? So it's just going to be kilopascals divided by kilopascals times by kilopascals squared, kilopascals cubed. That will give me 1 over kilopascals squared, and that is the same as kilopascals to the power minus 2. Then it says 6.4, and then, yeah, that's it. So more carbon monoxide is added to the mixture in question 6.2. The new mixture is allowed to reach equilibrium at temperature T. State the effect of any on the partial pressure method on the value of Kp. More carbon monoxide is added to the mixture. Effect on value of Kp, no effect, because only temperature can affect the value of Kp. Only temperature can affect the value of Kp. Effect on partial pressure of methanol. Well, if more carbon monoxide is added, what's going to happen to the, the partial pressure of methanol? Well, if that's more added, the equilibrium can shift and it's going to add more of this, so that will increase as well. That increases. So you should probably definitely get this right. This one is a bit more tricky, but it's still not that tricky. 6.5 says the effect of any addition of a catalyst in the value of Kp, no effect, like I wrote before. And I'll do it again just to reinforce the idea that only temperature can affect the value of Kp. And it's the same with Kc. Only temperature can affect the value of Kp. Reasoning, it's because, I will do it now, it's because catalysts increase the rate of forward reactions and reverse reactions equally, hence no effect. Increases the rate of forward and backward reverse reactions equally, therefore it's not going to have any effect. Question 7. Melting point of XeF4 is higher than the melting point of PF3. Explain why the melting point of these two compounds are different. In the answer, give the shape of the molecule, explain why each molecule has that shape, and how the shape influences the forces that affect the melting point. Now, obviously, if you learnt reviewed your bonding stuff and electron pair and all that. It should be a nice question, really. And if you didn't, an exam, you had this question, then yeah, it's not going to be very nice for you. So XeF4, well, it has 4 bonding pairs and 2 lone pairs around Xe. PF3, 3 bonding pairs and 1 lone pair around P. Stage 2, explanation of shapes. XeF4 is square planar. PF3 is pyramidal. And it might want me to draw it out as well, so let's draw it out. So Xe, just very simple diagrams. 4 bonding pairs, 2 lone pairs. And you know, these 2 examples are on my textbook, the CGP textbook. So yeah. So the first thing you should do with this topic is firstly, obviously, memorize all of these in your textbook, and then memorize the method and how to, find out how many bonding pairs and lone pairs it has. Because sometimes they just use textbook examples, and if they don't, then you know what to do as well. But if they do, you already learnt it off by heart beforehand. There you go. Now the explanation, well, I know electron pairs repel as far as possible. Or I could say, which is probably more common to say, lone pairs repel more than bonding pairs. And then stage 3, well, what is stage 3 about? It's about the intermolecular forces, because in the question it says why the melting points are different. So I'm going to have to talk about the intermolecular forces. So XeF4, what forces does it have? It has van der Waals forces, whereas PF3 has dipole forces. And now the rest of the question, the rest of the stage is going to be very easy. Once you identify the intermolecular forces, then you can ramble on about what that means. Well, stronger intermolecular forces in XeF4 due to a larger MR / more electron. Now, why doesn't XeF4 have dipole forces, you may ask? Because look at it, it's completely symmetrical. If I go here, completely symmetrical. If I go here, completely symmetrical. It's completely symmetrical. Whereas PF3, it's not. Yeah, it's not. Because of, yeah, it's not completely symmetrical. Therefore, it's got dipole forces. Whereas XeF4, because it's completely symmetrical, the dipoles will cancel out. Therefore, it won't have dipole forces. Question 8. Question 8. Question 9. Question 10. And question 11. Which I don't think I can do the question 11, but question 8. Use all the information, calculate percentage by mass of NaClO in the original bleach solution. Give your answers to 3 significant figures. So I know that okay, so first thing I can do is find out the moles of S2O32 minus. This is going to be 33.50. 30 divided by 1000 times by 0.100. And that will give me 0.00335. Then I know, because that is a 2-to-1 mole ratio, I can work out the moles of iodine. The moles of iodine is just going to be 0.00335 divided by 2. I'll just leave it like that. Then what do I need to do? Well, now I know ClO minus and that. It's the same amount of moles with 1-to-1 mole ratio. So, therefore, the number of moles of ClO minus is also going to be 0.035 divided by 2, which is 0.01675 moles. But now you need to read it back extremely thoroughly. And 9 times out of 10, they always have this trick. Transfer 25 centimeters cubed dilute bleach solution to conical flask. And then the first thing it says, dilute 10 centimeters cubed to 100 centimeters cubed with distilled water. So that's the number of moles into 25 centimeters cubed pipette. I want the number of moles overall in the flask, 100 centimeters cubed flask. So therefore I need to times it by 4. That's the tricky part. But they always like to include that part. So hopefully if you practice enough of these, you should spot it by now. Then the fourth thing I need to do now is, I've got that, now I can work out the mass. Because moles is mass over MR, mass is going to be the moles, which I just worked out, times by the MR of NaClO, because that's what I'm trying to do. So NaClO, and I should get 0.499 grams. Just doing moles mass of MR mass and moles times by MR. Simple rearrangement. Now, I also know that a density of original bleach is that, and I know transferred to 100 centimeters cubed, to 10 centimeters cubed sample of bleach solution. So that's of the bleach solution, and the density of bleach solution is that. Well, I can use density as mass over volume. Therefore, the mass is going to be the density 1.20 times by the sample of the bleach solution, which is just 10. And this is a part which caught me off guard. I converted this to moles per liter minus cube, but if you look at it, it says grams per centimeter cube, so both need to stay in the same unit. So you should get 12. And therefore, the final answer is going to be 0.499 divided by 12 times by 100, and you should get 4.16%. Just a lot of steps. Identify moles concentration volume. You need to use moles concentration volume. You need to use moles mass over MR. You need to use density mass over volume. You need to be able to rearrange those three. You also need to highlight the key information, understand which volumes for which. And this is a question, but it's giving you the equations. A lot of them, they don't even give you the equations. So yeah. Question 8.2, the total uncertainty from two readings at endpoint error in using burette is 0.15. What is the total percentage uncertainty in using the burette in this experiment? In using the burette. When I know it's going to be 0.45%. Question 9. State was observed in silver nitrate solution added sodium fluoride. Sodium fluoride. Colorless solution. So one observation was solid sodium chloride reacts with concentrated sulfuric acid. White fumes of gas. White fumes, we just say. And this is a perfect example for me and for you guys why you need to know your observations and all of that. Because look at that. 9 marks for basically what it looks like all AO1 questions. Equation when solid sodium chloride reacts with concentrated sulfuric acid again. It's just going to be NaCl plus H2SO4 arrow NaHSO4 plus HCl. Role of chloride ions in the reaction. It's a base, we could say proton acceptor. Given the reaction for redox reaction between solid sodium bromide and concentrated sulfuric acid. For the redox reaction, so now we need to think even more deeply which equation this is going to be. Recall it, and it should be this one. Plus 2H2SO4. And this reaction I'm going to form SO2 as well as Br2, Na2SO4 plus Br2 plus SO2 plus 2H2O. Why this is a redox reaction for 2 marks? Because I'm guessing the equation is only for 1 mark. I don't think it'd be for 2. So the explanation is 2 marks. So I'll talk about the oxidation state. So Br changes from -1 to 0 and is oxidized. And then I'll talk about sulfur changes oxidation state from -8 plus 2 minus 6 plus 6, from plus 6 to -8 plus 2 minus 8 plus 2, no, minus plus 4 to plus 4, and is reduced. I should say here again as well, changes oxidation state, be very specific. What was observed when aqueous chlorine is added to sodium bromide solution given the ionic equation for the reaction? Aqueous chlorine, sodium bromide. Yellow solution. Given ionic equation, chlorine plus 2Br minus 2Cl minus plus Br2. Use the equation to calculate and the data in table 5 to calculate Gibbs free energy change for reaction. And then it says use the data to calculate entropy change for that and what it shows about the feasibility of the reaction. Okay. And that's the end of question 9. Question 9 basically all A1 question, which is nice if you know it, but for me I didn't really know a lot of these observations equations, so I need to review them. So this should be pretty easy. Calculate Gibbs free energy change. It should be pretty easy. Well, firstly, recall Gibbs free energy change. Delta G is delta H minus T delta S. And first thing I need to do is work out delta F. Well, delta F, I'm working with formation data. You see that little F there? That means it's formation data. So entropy of products minus reactants. So minus 201 plus minus 242 minus entropy of reactants minus 394, and 0 is an element by itself, so it's going to be hydrogen, sorry, is going to be 0 anyway, so don't need to really include it. It's going to be minus 201 plus minus 242, and then do that minus 304, sorry, 394, yeah, minus 49. Clear, that's a 9. And that's in kilojoules per mole to power minus 1. And that's really important because I'll explain why in a bit. Then I need to work out delta S. Well, delta S is entropy of products minus entropy of reactants. Entropy of products minus entropy of reactants, which is just going to be, obviously I'm going to show all my working because it is 6 marks. In the exam, definitely always show you working, and I'm going to do it as well for this case. So if I get the answer wrong, then I can see what happened wrong. Minus entropy of reactants 214 plus 131. There's one thing I didn't check, any moles. There we go. So that's another mistake I was about to make. If I put in a calculator, got 3 moles of hydrogen. So this value of H2 needs to be times by 3. What I'm going to do is I'm going to do it step by step. So that's going to be 427 minus 214 plus 131 plus 131 plus 131. 607. 427 minus 607 minus 180. Does that make sense? Yes, we go from 4 moles to 2 moles. So minus 180, and it's in joules K to power minus 1 mole to power minus 1. Now I need to add a spot. I want my final answer in kilojoules mole to power minus 1. I've got delta S in joules, so I need to divide it by 1000, aka times by 10 to power minus 3. Then I can substitute an equation now. Delta G is delta H minus 49 minus T, the temperature. It does give it me in Kelvin. I don't need to convert it, so that's minus 980 bracket minus 180 times by 10 to power minus 3. Minus 890 and I get 111.2. Perfect. And I'll just say 111 kilojoules mole to power minus 1. Find out delta H minus 49 kilojoules mole to power minus 1. Find out delta S minus 180 joules K to power minus 1 mole to power minus 1. Delta G is delta H minus T delta S. Substitute the equation, but remember, delta S needs to be in kilojoules, so I need to divide by 1000, and then I get my final answer as 111 kilojoules mole to power minus 1. Okay, and then figure 4 shows how the Gibbs free energy change varies with temperature in a different gas phase reaction. Straight line graph for this gas phase reaction will be extrapolated to 0 Kelvin. Use the values of intercept and gradient from graph in figure 4 to calculate enthalpy change in this and entropy change. So how do I do this? Because now I see these more and more often graphical questions. So they'll give you this, I'd say pretty nice 6 marker, and then a graph question for 4 marks. So I've got delta G here, temperature here, and I want to find out, well, if I find out the gradient of the graph, okay, first things first, I want to use the values of intercept. So the intercept is here, intercept of the y-axis when x is equal to 0 is here, and that is 145. So I know delta H, yeah, because delta G is delta H minus T delta S. So first thing I would actually do is y equals mx plus c, because it's a straight line graph. Delta G equals delta H minus T delta S. But there's something wrong, because that's minus T delta S, so I'm going to rearrange it. Delta G equals minus T delta S plus delta H. So I can clearly spot this is delta H. So delta H equals C. And how do I find C? Well, that's the y-intercept. And how do I find y-intercept? That's when x is equal to 0. So that's 145. So now I've got delta H. I've got C equals 145. Therefore, delta H equals 145. Okay, that's nice. And obviously the unit's kilojoules per mole to power minus 1. Then I want to find out, I've got the delta H and the entropy change for this reaction. Well, the entropy change is mx, right? And if I find the gradient, I will get, if I get the gradient, I will get minus delta S. Okay, so that's it. So all I need to do now is find out the gradient. And remember that is equal to minus delta S, because minus T delta S. T is X. I don't care about T. I want the entropy change. So yeah, find out the gradient. Just do your typical y2 minus y1 divided by x2 minus x1. And then the final step is I want my answer in joules k to the power minus 1 mole to the power minus 1. This gradient will give me in kilojoules mole to the power minus 1. So delta H is 145, that's really nice. And once I've done the gradient, and you times it by 1000, obviously the gradient is minus delta S, so then divide by minus 1, and I should get 167, which is obviously positive. And you know, I probably should have went through how to do it. I'll go through it as well now. Why might as well. Yeah. So I had to find out the gradient. So I just picked 2 points. Let's say the 2 final points. Okay, so y2 minus y1 over x2 minus x1. y2 145 minus minus 55 minus 60 65 70 minus 60 minus 60 divided by x2. That's the change in y. We draw a triangle like that. The x2's 0 minus 1200. And yeah, you get 170 in this case, plus 170. Once I've times it by 1000 as well, and the mark scheme allows 167 to 173, so 170 would be perfectly fine, positive 170. So not too complicated. My advice for this kind of question, graph question, delta G and all of that. Y equals mx plus c is a straight line. Compare it to Gibbs free energy change, and then you can work your way from there. And remember, the units always try to convert delta S. State what figure 4 shows about the feasibility of the reaction. Figure 4, not my answer, figure 4. So figure 4 is here. So the feasibility of the reaction, Gibbs free energy change. Gibbs free energy change can only be feasible if delta G is less than 0. Now if I look at delta G here, it is feasible above this temperature. And what is that temperature? Above 8, 20, 40, 60, 80, 90, yeah, so no, 900, sorry, 820, 840, 845, and 845, yeah, so that's all I have to say, but I have to be very specific in this case. So, above 845 Kelvin, the reaction becomes feasible, and below 845 Kelvin, the reaction is not feasible, or not thermodynamically feasible. Because if you think about this, if it's feasible here because delta G is negative, well, if it's below this temperature, delta G is always positive, so it's not going to be feasible. And that is the end of question 10. And question 11 I can't do since I haven't gone through it. So that is the end of this paper.